Mr. Ryan. Are you alright?
Cool.
Yeah?
Yeah.
Okay, so remember what we talked about yesterday? The
Only try.
counting only try using
Yeah.
which algorithm?
Breakfast.
Breakfast search.
Yeah.
Yeah. Okay. We are counting this only try using the breakfast search, okay? So how are we implementing this breakfast search?
Level by level.
Level by level. And what kind of data structure are we using to implement the breakfast search?
Queue.
Yeah, and the queue is first in.
First out.
And in Python, what function, what class name is used to implement the queue?
DQ.
DQ. What does DE stand for?
Double-ended.
What does it mean by double-ended?
You take it out and you put it on the end.
Okay, so basically double-ended. So it means that I can
Two sides.
two sides. Yeah, well done. So I can append and pop from both sides. Okay, and then the complexity to push and pop from both sides is what? What's the time complexity? Constant time, right?
Yeah.
Constant time. So it means that it's very quick. Okay. If you are popping one element from the beginning of a list, list. Remember in Python we're using this to represent the list. If we pop the beginning of the list is pop 0, yeah? Pop 0. It takes linear time, right? But in DQ, you can use the pop left, which is 01 constant. So this is better. So that's why we're using DQ instead of list to achieve the queue thing, okay? So the counting only child using the breakfast search. Yeah, we put it in the queue and we take it out.
The time complexity is O(n).
Yeah, when n is what? The number of nodes in the binary trees, yes.
Yeah, the same for depth search.
Okay.
It's the same.
So look, the key important things to take away here is that we are pushing the node together with the number of children for its parent, right? So then when we expand the node in the next level, we can accumulate or we know which are the only child by checking this counter. If it's 1, then it means that its parent has only one child, which is itself, right?
Yeah.
Okay.
Then you put it.
Yeah. We can put it in the answer or answer. If it's a integer to count how many only child, we can just increment 1. Or if you want to get the list of only child, you can put it in the list, right? And then you can count it using the length function. Okay. Basically, that's what it is. So we can also solve this problem using the depth first search. Yeah. So can you tell me what's depth first search?
Go as deep as you can.
Okay, I'm going to do one example. Okay, so you tell me what are the depth first search?
I will add some more.
Okay. Wow. Okay, so what's the depth first search of this? If I want to perform the depth first search of this file.
1, 3, 8, 9, 7, 5, 12, 10, 11, 3.
10, 12, and this.
Just
8 and 11, 13, yeah? Okay?
yes.
So the depth first search is go left as much as you can. If not, you retreat, and you go to the right. And then finish it, you go retreat, you go to the right, go to the left, yeah? Okay? So using the depth search.
big tree.
Yeah. Using the depth first search, we need to remember passing down the number of the child of the current node, right? So in the next level, we can check this counter. If it's 1, then we accumulate this, right? Alright?
Yeah.
Okay. So you tell me, okay?
I tell you.
Depth first search, let's say define depth first search root, and then we also need a counter, right?
Yeah.
What does this counter mean? Can you tell me? What's missing?
Column.
Okay.
Oh,
So look, if root, okay, I asked you about the counter thing. So what does it mean? Counter thing.
that sound was funny.
What does the counter thing mean?
That counts stuff.
Yeah, count stuff. It means that the number of the counter means what? Look, it means the parent of the root. Yeah? Alright? The parent of the root has how many children. That's for the counter mean. Does it make sense?
Yeah.
Okay, so if root is none, what should we return?
0.
Yeah, it means that nothing. Yeah, it doesn't have any only try kids.
0.
Okay, so look, if we have a counter here, yeah. So look, answer. Let's say answer equals 0 first, right? And then look, if counter equals 1, right? If its parent, right? If its parent has only one kid, then we increment the answer here. Answer plus equals 1, right? Yes? Does it make sense? Okay, then what should we do? This function will return the number of the one only child in this root tree, in this subtree. So we also need to add answer equal plus equal what? Alright, can you write it here? This is root of left. Root of left, and then what?
I think.
Okay, we are missing something here. Okay.
Counter something?
So no. First of all, let's say we are now reaching the root node, right? But now we want to know how many kids current node has, right? Let's call it x, okay? X equals 0. Then if root the left, okay, so current node has the left child, right? So x plus equals 1, right?
Yeah.
Yeah. And then what's next?
1 plus 1 equal 2.
I check on the left, and I also need to check what?
Right!
Then
If we got right column and x something.
And what? And what?
And equal 1.
X equals 1. So what does this x mean? What does this mean? Can you tell me what does this mean?
I think x.
X, what does x equal? What does x mean? What's x mean? Why are we calculating the x? What's x mean?
X means like
The number of what?
stack?
No, we're currently at root. So what's root? Look, if root is left, then x will be 1. If root right, and x will be plus 1, right? So it means x is what? The number of what?
The number of notes.
Of-
The number
Of
of notes that root.
has.
Yeah.
The children knows, yes. Okay, so look, yeah. And then now, I know this x, yeah? Then I need to answer plus equal that first search. Then we are counting, we recursively counting what? Left tree, yeah? Root of left, and what should I pass this count here? What should I pass in this? What should I pass here? We are counting the left tree. It's left tree with, look, remember this CNT, what does it mean?
Counter!
What's this CNT mean? Root of left. What's the parent? What's the parent of root of left? What's the parent of root of left? Come on. Root. Okay. And then the number of the children of the root is what? What are we?
Or 1.
So yeah, what we are calculating before. So what should I pass this value? Come on.
1.
1. Why is 1?
Well.
Answer plus equal depth first search, and then that will be root of what? Root of what?
Right.
Right. And then again.
Answer!
What do I pass here? The second parameter. Come on. The CNT I just said is the number of the
The
kids
number of the
for the
kids
root's parents.
for the root's parents.
The number of root of left. The parent is of root of left, or the parent of root of right is root, yeah?
Yeah, root.
And the number of the kids for the root is what? Come on, it's there.
The number of the kids for the root.
Yeah, the number of kids of root is right there.
X!
X, come on, how high would that be?
It says 0.
And what's missing here? The last letter.
Return!
Return what?
Answer.
Well done.
Yay!
The answer. Yeah, does it make sense?
Gymnastics.
Does it make sense? No. People will watch you all over the world. Okay, they don't want to see your feet. Okay. So when we are calculating the root, so the first CNT we can pass any number like 0, -1, as long as you don't pass the 1, right? Yeah, because the number of root parent kid is 0, right?
Yeah.
Yeah. There's no parent of a root, right? Root is the only node in a binary tree which does not have what?
Which does not have.
Have what? I'm just testing you if you're listening.
Which does not have root. No.
Root is the only node in binary tree.
It does not have a parent.
That's right, yeah. And the leaf nodes are the nodes in binary tree which does not have what?
Which does not have children.
Well done, okay. Well, that's fine. Okay, what's the term complexity?
N.
What's N? What's N?
The number of nodes in the binary tree.
Well done, well done. So which one is better? You think the depth first search or breadth first search?
They're both the same complexity.
Yeah, and which one you think is more easy to implement? It's easier to implement. Breadth first search. In breadth first search you need to implement the breadth first search using the queue, right? But here we don't use the queue. We use the stack. But there is no stack here. So how are we going to use? Where are the stack here?
No.
There's no stacks, but there's recursion. When we talk about recursion, the computer maintains the stack for you. Does it make sense? Okay, so you can implement this depth first search without the recursion, but in that case, you need to do a stack, and then you'll be more complex. That's why we prefer using the recursion. The computer will maintain the stack for you. Okay, so what does it mean? If there's a stack, what's the space complexity? What's the space complexity? Yeah, well done. Okay. Okay, let's see. I'm going to erase the. No. If you're looking, I'm not.
No.
Okay, I'm going to.
This.
Okay. That's it. What's here? What's here?
Zero.
What's here?
Let me check.
So answer equals 0. So what happened when?
Answer. If.
What? If what?
If.
What answer is the number?
C and T.
Yeah, if C
Equal 1.
Yeah.
Equal 1.
And then what? And then what? And what happened? And
Answer plus equal 1. X equals 0. X equals 0.
X equals 0. Okay.
Yeah. Yay.
What does it mean? What does it mean, Eric?
It means that.
What does it mean? Why are we doing this?
Right.
What's this bit? What's this bit?
Because the answer starts at 0. Yeah.
If counter is 1, then we found.
Then we found it.
Found the current node is the only track. Then we add it.
Yeah, add it.
Add 1 because we're returning answer here. And then answers the variable we accumulate we keep counting the only track in its left subtree and the right subtree using recursion, eh?
Yeah.
Okay, that's it for today.
Yes.
That's it for today. Bye bye. Bye bye.